we'll work one example. There's 4 problems in the book that go over this also. So when we're done with this example, if you want to look at those problems, that would be a good idea, if you haven't already. So we want to use Euler's method to approximate the value of y at 0.5, given that we know that y at 0 is 2, and this differential equation here. So we know that the derivative of y with respect to x is equal to y minus x. And we're going to use increments of 0.1. So what this means here is we're going to go by 0.1 along the x-axis 5 times to go from 0 to 0.5. Does that make sense? So essentially what we're doing is we're going to find the linear approximation of y at 0.1, and then we're going to use that value to find an approximation of y at 0.2, and then use that to find an approximation at 0.3, and then at 0.4, and then finally at 0.5. So we're going to take a few steps to get there. To organize our work, I'm going to put all of my work here in a chart. And the idea here is that the change in y, as long as the change is small enough, the change in y is going to be approximately equal to the derivative times the change in x. Now, in this example, what's the change in x going to be? 0.1. And then we're going to use this to figure out what the change in y is, and we know what the derivative of y with respect to x is. That's given to us. That's this differential equation here. So like I said, we're going to organize this in a chart. Let me take a second here to make the chart. Again, we've got 4 things here in our chart. We've got the x values, the y values, and these y values are approximations of the y given by this differential equation. They're not going to be exact values after this first one. Then we're going to evaluate the derivative at this point, 0, 2 to start with. That's going to give us our delta y when we multiply by our delta x, which is going to be 0.1, and then we use that delta y to get our next one. So what is the derivative here going to be? And this is something, this will be on a calculator section of the test, so this is something you can just plug into the calculator. This one's pretty easy, I think. Y minus x here is 2 minus 0, which is what, Cole? 2. That's going to be 2. So our delta y then is going to be 0.1 times 2, which is 0.2. So at this point, at the point 0, 2, that means that we have a slope of 2 at that point, and so moving by 0.1 along the x-axis is going to be the same as moving by 0.2 along the y-axis. So how do I find the new y value here at 0.1? Yeah. So we take the previous y value, this 2, add on our delta y to get our new y value. Remember, delta y just means change in y, right? So if y is changing by 0.2, it's going to go up by 0.2 and we get to 2.2. Okay, now we need to get our new derivative. So at this point, at the point 0.1, 2.2, what's the derivative going to be? How'd you get that? Okay, I'm gonna write the math in here a little bit. So it's going to be 2.2 minus 0.1. That's our y minus x, and that's going to be 2.1. Then our delta y is going to be 0.1 times 2.1, which is so we're going to get 0.21 here. All right, so our y value at 0.1 is 2.2. So what's our y value at 0.2 going to be? Yeah, it's going to be 2.2 plus 0.21, so it's going to be 2.41. To get the next derivative, we would take our y minus our x, and hopefully you got 2.21 for that. And then we multiply that by 0.1 to get the next delta y. So then we take our last y value, our previous y value, plus our delta y to get 2.631. And then we use that. We take 2.631 minus 0.3 to get our new derivative at that point. And then we'll multiply that by 0.1 to get our new delta y. And then we do it again. We get 2.8641 for our y value at 0.4. Plug that in to get the derivative. 2.8641 minus 0.4 would give you 2.4641. Multiply that by 0.1 and we get our delta y. And at this point, once we add on our delta y, which I did the math here in the column, once we add that on, we're done. So this is our approximate value right here of y of 0.5. Now, why is this method better than linear approximation? Why would it be more accurate? This is what the linear approximation looks like. So what we did, and this drawing is probably going to be too small here, but I'll try to give you the idea at least. What we did is we did linear approximations with small steps. So we said, okay, it has a slope of 2 for a short period of time, but then it's going to have a slightly bigger slope for another period of time, and then a slightly bigger slope for another period of time. And so we get a slightly larger answer. I know I didn't do 5 steps there, but you get the idea. So we've got tiny segments there that each one of those segments is a better approximation of the curve than our line was, our linear approximation was. Does that make sense?
Yep.
Okay.